Here is another example on linear programming. So you're about to take a test that contains computational problems and word problems. The computation problems are worth 6 points and the word problems are worth 10 points. So naturally the goal here is to maximize the score. And the goal is to maximize. We don't want a minimum score, we want to maximize it. And I'm going to define x to be the number of computational problems and y to be the number of word problems. And 6 of x, so 6 points for each computation problem, and 4 times y, 4 points for each word problem should maximize the score. I take that back, it's actually 10 points for a word problem. Now, there is the first constraint that you can do a computational problem in 2 minutes and a word problem in 4 minutes, and you have 8 minutes to take the test. So the time constraint is 2 minutes per computational problem, so 2x, 4 minutes per word problem, 4x. The total time is 2x plus 4y, and it has to be less than or equal to 8. If I rewrite this, I would have 4y less than or equal to 8 minus 2x. Divide by 4 on both sides, y is less than or equal to 8 over 4 minus 2 over 4x. So y would be less than or equal to 2 minus 1 over 2x. And if I rewrite it in slope-intercept form, we have minus 1 over 2x plus 2. And there is another constraint on the number of questions that you may not answer, or you may answer no more than 5 problems, which is right over here. So the total number of problems, which is the count, x plus y has to be less than or equal to 5. And if I rewrite that, y is less than or equal to 5 minus x. In slope-intercept form, that would simply be minus 1 times x plus 5. So we have our constraints, we have the objective function, so let's maximize the score. And naturally, there are 2 other constraints. X has to be greater than or equal to 0, and y has to be greater than or equal to 0, because we can't have negative scores. So everything is going to happen in the first quadrant. So that said, I'm going to go for the first constraint, which is right over here. So the intercept, y-intercept is 2, and the x-intercept would be 4, and it is a solid line. And since it is less than or equal to, and I'm looking at the first quadrant, I'm just going to shade. There. The next constraint is y less than or equal to negative x plus 5. So the y-intercept is 5. And the x-intercept is 5 as well. Oh no. And the second line, it has to be less than or equal to, or y has to be less than or equal to the blue line that I just drew. So the only overlapping region here would be right there. So the feasible region would be those, and the corner points are 0, 0, 4, 0, and 0, 2. Now we can evaluate the objective function, which is the score, and we have that written as 6x plus 10y. So 0, 0, 4, 0, and 2, 0. So we have 6 times 0 plus 10 times 0, which is 0. 4 times 0 plus 10 times 0. Excuse me. 6 times 4 plus 10 times 0 is 24. And lastly, 0, 2. 6 times 0 plus 10 times 2 would give us 20. So how do we maximize your test score? We simply do So if we do 4 computational problems and no word problems, we get a maximum score of 24. Now, you can verify the answer by plugging in the values in the constraints. So we have x to be 4 and y to be 0. So does that satisfy the constraints that we have? Let's see. Is 4 plus 0 less than or equal to 5? Yes. So it does satisfy our second constraint here. And does it satisfy the other constraint, which is 2x plus 4y to be less than or equal to 8? So we have 4 times 2 plus 4 times 0 to be 8. So that is also satisfied. So the solution you have is correct. So here is the last example on linear programming. So a company manufactures bookshelves and desks for computers. The company's profits are 25 per bookshelf and 55 per desk. The company should not, so we're going to get into the constraints. So let's go ahead and write the objective function first. So Z would equal to 25 per bookshelf, and we have x bookshelves, so 25x plus 55 per desk, so it's 55y. Our goal is to maximize this manufacturing or quantity so that we make profit. So that is the objective function. Now we have to go to the constraints. So the company should not manufacture more than a total of 80 bookshelves and desks per day. In other words, the number of desks, y, plus the number of bookshelves, x, must be less than or equal to 80. And to meet the customer demand, the company must manufacture between 30 and 80 bookshelves per day, inclusive. In other words, 30 has to be less than or equal to x, which has to be less than or equal to 80. And the company must manufacture at least 10 and no more than 30 desks per day. So at least 10 would mean y is greater than or equal to 10, and no more than 30 would mean x is less than or y is less than or equal to 30. So if I combine those, we have 10 less than or equal to y less than or equal to 30. So we have our constraints. So the constraint would be that, and naturally we have x to be greater than or equal to 0, y to be greater than or equal to 0, because we cannot manufacture negative number of items. So x and y, they have to be positive, but they can be 0 also. But if it is 0, you're not making any profit. So we have to draw the constraints, and everything is going to be in the first quadrant. So that is the first quadrant. So I'm going to have 0, 20, 40, 60, 80, 100, 20, 40, 60, 80, 100. And the first constraint is x plus y less than or equal to 80. So that would be a third constraint. The first one is 30 less than or equal to x less than or equal to 80. So I'm going to draw a line here. And constraint number 2 is that y is between 10 and 30, including and 30. So constraint 1 restricted us to that region. Constraint 2 is putting us there. And constraint 3 states x plus y is less than or equal to 80, which would mean y is less than or equal to 80 minus x. In slope-intercept form, that's simply -1 times x plus 80. So 80 is the y-intercept, and the x-intercept would be right here. And we can draw a line through. And we have less than or equal to, so we're going to shade below the line. And that's good enough because the other two constraints restrict us to that particular region. So the corner points are those four, and the feasible region is that. So the first corner point right over there is 20, 10. The corner point over there is 20, 30. The corner point here would be 50, 30. And the last one here would be 70, 10. And if you can't get this directly from the picture, you could always plug it in the equation here and look for points of intersection between this line and the vertical lines x is equal to 20 and x is equal to 80. So the corners are 20, 10, 20, 30, 50, 30, and 70, 10. So we can plug this in the objective function, which is 25x plus 55y. So um, 25x would simply mean 25 times 20 plus 55y, 55 times 10. We have 500 plus 550, which would be 1050. The second case would be 25x, 25 times 20 plus 55 times 30. So that would be 500. 15 times 30 would be 1650. So we have 2150. And 25 times 50 plus 55 times 30. So that would equal to 1250 plus 1550. That would be 2,800. And lastly, we have 25 times 70 plus 55 times 10. So that would be 1750 plus 1650. That would put us at 2400. So where does the maximum happen? The maximum happens at the corner point 50, 30, and the amount is 2,800. And the maximum profit is 2,800. You can always verify the answer by going back to see if it satisfies the constraints. Is 50 bigger than 0? Yes. Is 30 greater than 0? Yes. So the constraints x greater than or equal to 0, y greater than or equal to 0 is satisfied. If we add x and y, is it less than or equal to 80? 50 plus 30 is less than or equal to 80. Is the value of x between 30 and 80? 50 is between 30 and 80. Is the value of y between 10 and 30, including 30? Yes. So everything is satisfied, so we have the right solution.